Welcome back to Series on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to the channel for future videos and notifications. Alright, in this video we're going to look at two more examples of the alternating series test. We already did 2 or 3 in the previous videos, alright? So let's do 2 more. Here we have a series from n equals 1 to infinity of negative 1 to the n power times the quotient of the natural log of n and n. Alright, so the alternating series test tells us we need to know our b sub n. So what's our b sub n? We basically just remove the alternating part of this series, which is the negative 1 to the n power. So our b sub n is just the natural log of n over n. So now that we know that, we need to test these 2 criteria. That's the alternating series test. So let's take the limit as n goes to infinity of our b sub n and see what it does. So the limit of n goes to infinity of natural log of n over n, well, this is indeterminate form because the natural log of infinity is infinity, and in the bottom we just have infinity. So the best option would be to do L'Hopital's rule. So let's take the derivative of both the numerator and denominator with respect to n. So L'Hopital's rule says the derivative of the natural log is just 1 over n. We still have the limit as n goes to infinity, and the derivative of the bottom, n, is just 1. And so this would just become the limit as n goes to infinity of 1 over n, which if you plug in infinity, 1 over infinity is 0. So yes, the first criterion is satisfied here. All right? So let's move on to the second one. In this case, we're actually going to have to use a little bit of Calculus 1 skills and some derivatives. So we have to actually determine whether or not this is a decreasing function. So in a lot of cases, you can simply just plug an n plus 1 in for n and test to see whether that's smaller than just b sub n. That's a lot harder to do here since natural log of n plus 1, there's not really a good way to evaluate that. So if we're trying to prove it's a decreasing function, then what we can do is actually just take the derivative of the entire function, ln of n over n. Let's just take this derivative, and notice we're going to have to use quotient rule on this. So quotient rule says we take the denominator times the derivative of the numerator, so n times 1 over n, right, minus the numerator times the derivative of the denominator. All right, so it's natural log of n times derivative of n is 1, and then divided by the denominator squared, so n squared is just n squared. Remember, if you're doing quotient rule derivatives, a good mnemonic is low d high minus high d low over low low. That's the way I always learned it in Calculus 1. So low d high is the derivative of the high one, which is the numerator, minus high d low is the derivative of the denominator. All right, so using quotient rule here, notice n times that 1 over n is just 1, and then minus ln of n, so minus ln of n over n squared. So what does this mean? Well, this 1 minus ln of n over n squared, this is actually the derivative. And so if we want to know if it's decreasing at any place, we need to basically plug in numbers here and have the whole thing come out negative. Because if we evaluate the derivative at any point and it comes out negative, that means it's decreasing because the slope is negative, right? So what we're going to do is we're going to solve this for 0 because we'd like to know what points at which the derivative is negative. All right, so we set this equal to 0. So 0 is equal to 1 minus ln of n over n squared. Now if we multiply both sides by n squared, that goes away. So the n squared doesn't matter. So 0 equals 1 minus ln of n. If we add ln of n to the other side, we get ln of n equals 1. And so n would be e. All right, so our critical point is when n is equal to e. Now, let's just plug in a number greater than e. So let's do 3, because e is like 2.7 something. So let's use 3. So 1 minus ln of 3. Well, ln of 3 is a number greater than 1. So we'd be doing 1 minus a number greater than 1. So this whole thing will end up being negative, basically when n is greater than e. All right? And if we plug in a number less than e, let's say 2, so if we plug in ln of 2, that's a decimal. It's like 0.69 or something like that. Well, 1 minus 0.69, whatever, that's a positive number. So less than e, this whole thing turns out to be positive. All right, so if we think about it, what integer numbers are included in the series? Well, it has to start with 1, and then it's just 1, 2, 3, 4, and so on and so forth. Well, if we look at n equals 1 and 2, this whole thing is positive, but anything 3 or greater, it's going to be negative, all right? Now this is an important point with the alternating series test. This statement, b sub n greater than b sub n plus 1, or it's a decreasing function, that does not have to be true for every single number. You can have it start out increasing, okay, which it is here. It's increasing for basically everything less than e. That's fine, as long as it decreases at a certain point out to infinity. So if we have a number 3 or greater, it is decreasing, so therefore this is a decreasing function. ln of n over n is decreasing. So as long as it eventually decreases, you're fine. And so the reason we wouldn't put n is greater than or equal to e for this is because we're only using integer values, so it has to be 3. All right? So the point is, the limit as n went to infinity of b sub n was 0, and it's a decreasing function. So we passed both of these criteria. Therefore, this original series converges, but we still don't know whether it's absolutely convergent or conditionally convergent. So therefore, what we have to do is we have to take the absolute value of this series. So we take the series from n equals 1 to infinity of the absolute value of negative 1 to the n times ln of n over n. And ironically, of course, since we're taking the absolute value, the alternating term goes away, and we're just left with the series from n equals 1 to infinity of ln of n over n. Now, we actually need to determine whether or not this series converges or diverges, and we can use any test we want. Well, let's think about this for a second. This series looks somewhat similar to the harmonic series, right? Because 1 over n is the harmonic series, so probably a good bet would be the comparison test, or direct comparison test. So let's look at our series, n equals 1 to infinity of ln of n over n. Alright, so in this case at least, my a sub n is ln of n over n, alright, right over here. And the series b sub n, which is what I'm comparing it to, is just 1 over n. Now, if written as a series, which I have here, this is the harmonic series, which we already know diverges. So if I can prove that this series, ln of n over n, is bigger than the harmonic series, then it diverges, because it's bigger than a divergent series. So is it true that the series from n equals 1 to infinity of 1 over n, the harmonic series, is less than the series from n equals 1 to infinity of ln of n over n? Well, let's think about it. So we can use the criteria that we found in the previous part of the test, where n had to be greater than or equal to 3. So if we think about if n is 3, if we take an ln of 3, that's a number bigger than 1. All right? So we'd have a number bigger than 1 over 3 is bigger than 1 over 3. If we do the same thing for 4, ln of 4 over 4 is bigger than 1 over 4, since ln of 4 is bigger than 1. All right? So for n greater than or equal to 3, this is true, okay? That this original series right here, which is the absolute value of the alternating series, is bigger than the harmonic series, which diverges. Therefore, this series, the series from n equals 1 to infinity of ln of n over n, diverges. It diverges by the comparison test. Therefore, because the absolute value of the alternating series diverges, the original series is conditionally convergent. Remember, because the absolute value of the original alternating series diverges, that corresponds to conditional convergence. The only way you can have absolute convergence is if the absolute value of the original series converges. And we haven't seen one like that up until this point. Alright, here's our alternating series. It's the series from n equals 0 to infinity of 1 divided by negative 1 to the n, 2 to the n, plus 3 to the n. Now, it may not be apparent, and you can actually show this, although I won't do it here. If you have an alternating term, especially a negative 1 to the n or something like that, where it's negative 1 in the denominator, you can basically just flip that into the numerator and it doesn't change the value. So I can equally write this original series as the series from n equals 0 to infinity of negative 1 to the n divided by 2 to the n plus 3 to the n. All right? Now, the alternating series test requires us no b sub n. So our b sub n, we just take out the alternating part. And so our b sub n is just 1 over 2 to the n plus 3 to the n. All right, let's look at the limit as n goes to infinity of 1 over 2 to the n plus 3 to the n. Well, I think it's pretty obvious if you plug in an infinity to either of these n's. 2 to the infinity is infinity, plus 3 to the infinity is also infinity. This whole thing is just 1 over infinity, which is definitely 0. So good, our first criterion is passed. Let's go to the second one and see if this is in fact a decreasing function. Alright, so we have here our b sub n, 1 over 2 to the n plus 3 to the n. We would need to prove that that's bigger than our b sub n plus 1, which would just be 1 plus 2 to the n plus 1 plus 3 to the n plus 1. Alright, let's look and see what this term is actually equal to. So 1 over 2 to the n plus 1 plus 3 to the n plus 1. I can actually break up both of these exponents. So the 2 part becomes 2 times 2 to the n, right? 2 to the n plus 1 is equal to 2 to the n times 2 to the first. So the 2 to the first is just pulled out in front. So I didn't change that. I can do the same thing to the 3 to the n plus 1 part. That becomes 3 to the n times 3 to the first, or 3. Okay, now to show that this is decreasing, I have to ask myself, is 1 over 2 to the n plus 3 to the n, is that still bigger than 1 over 2 times 2 to the n plus 3 times 3 to the n? Well, let's just think about each of these terms independently. If you plug in a 1 here, 2 to the first is 2, right? So over here I'd have 2 to the first, but then times 2. So whereas this first term would be 2 over here, this one would be 4. Over here, if I plug in 1, this would be 3, and this one would be 3 times 3, or 9. Alright, so what that means is that for every single term in this series, 0 to infinity, the denominator over here is actually going to be smaller, because I'm not multiplying by these coefficients in front of each of these terms. So because the denominator over here is smaller on the left, overall this term is bigger. And so therefore, b sub n is decreasing. Alright, so we've just satisfied both of these criteria, and that tells us that this alternating series does converge. But again, it doesn't tell us whether or not that series is conditionally convergent or absolutely convergent. So to do that, remember we need to take the absolute value of the alternating series. So if we take its absolute value from n equals 0 to infinity of negative 1 to the n over 2 to the n plus 3 to the n, that gives us the series from n equals 0 to infinity of just 1 over 2 to the n plus 3 to the n. Alright? Now, perhaps another good test to use here would also be the comparison test, or direct comparison test. Alright, so if I'm going to use direct comparison test, I need a b sub n to compare the original series to. So our b sub n, I'm just going to knock out the 2 to the n and just use the 3 to the n. So b sub n is going to be 1 over 3 to the n, alright? I'm just taking off the 2 to the n, but remember what I can do is, since 1 to the n is still just 1, I can actually throw the n outside of the fraction as an exponent on the whole thing. So 1 over 3 to the n is just 1/3 to the n power. And here's this written as a series. It's n equals 0 to infinity of 1/3 to the n. This is a geometric series. That's actually very good. And actually, because the r of this, which is 1/3, because that's less than 1, remember for a geometric series, when this inside the parentheses, this r is less than 1, this series converges. Okay? So, in other words, my series from n equals 0 to infinity of 1 over 3 to the n, this is a convergent geometric series. So let's compare now this original absolute value series to that. So is the series from n equals 0 to infinity of 1 over 3 to the n, is that greater than the series from n equals 0 to infinity of 1 over 2 to the n plus 3 to the n? Well, in fact, this is going to be greater, because if you think about the denominators, over here on the right in the original absolute value series, I have an additional 2 to the n. So for every single term, for every value of n, this denominator over here is going to be larger. Therefore, this series, which is the absolute value of the alternating series, this one over here on the right is always smaller than this convergent geometric series. And because I have a series that's smaller than an already convergent series, then this absolute value series right here converges by the comparison test, and it does so for all values of n in the series. Okay? So, because I now got the absolute value of the alternating series to converge, now I have the original series, this one right here at the top, it is now absolutely convergent. Okay, and remember that's because the absolute value of that alternating series converged, and that correlates with absolute convergence. All right. So hopefully these two examples gave you even more of a grasp of the alternating series test. In the next video, we're going to do one more example, and we're going to see one that doesn't at first look like an alternating series, but it actually does alternate. All right, so please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.